Hello everyone, my name is Leo, and the topic I'm covering today is called No Training Data, No Problem, Weak Supervision to the Rescue. This talk is based on my Medium blog post that you can access for free by scanning this QR code. It'll lead you directly to the post. I'll add a link to these slides in that blog post after this meetup, so if you want to refer back, you can always get it from there. Or you can ping me on LinkedIn too. I'll skip this slide since it was already covered. The agenda for today's talk is as follows. We'll first discuss about some challenges around contemporary machine learning, specifically around the need for massive labeled datasets. We'll then discuss the concept of weak supervision and how it alleviates the problem. Then I'll introduce a couple of very powerful open source weak supervision frameworks that you can use to implement weak supervision on your problems. They're all backed by solid research and have papers published very recently. Finally, we'll wrap up the talk with a conclusion and the direction I see this technology moving in the coming years. First, one of the big challenges that real-world machine learning models face today is the need for massive amounts of manually labeled training data, right? For example, the famous ImageNet dataset uh, that pretty much every computer vision model is trained on these days has about 14 million manually annotated images. With the advent of transfer learning techniques, this situation has improved drastically. We no longer need millions of label data, but most models still require a few hundreds to thousands of high quality hand labels to fine tune natural language processing models such as BERT. It's not uncommon that we collect 50 to 60,000 labels for training today's models. As you might have experienced or you can imagine, manual annotation is costly because most teams outsource labeling to an external vendor or crowd workers like Amazon's Mechanical Turk. It's time consuming and labor intensive to read each and every line before labeling. One of the major issues with human labeling is that humans are inherently biased and error prone. Sadly, natural language is very subjective and ambiguous many times. And finally, especially in the domains where knowledge of the task requires tremendous domain knowledge, say for labeling medical data or labeling legal data, it is difficult to get labels because the subject matter experts who have the knowledge to label have to actually run the business and they do not have the time to label data for your models. All that being said, unlabeled data is vastly abundant. We just don't have labels on them to train our ML models. Also, most organizations have a lot of domain knowledge locked up in people's brains as tribal knowledge or some heuristic rules or search queries, etc. Unfortunately, most machine learning models these days ignore all this wealth of information and rely only on the labels from crowd workers or non-expert workers, right? So we ask ourselves the following questions. Can we leverage the wealth of domain knowledge in our organizations to label data? And can we do so in a programmatic fashion? Why? Because programmatically means we can run the labeling process on the entire corpus of unlabeled data that we have, even if it's millions of rows. And at the same time, the labels are generated from domain knowledge of our experts rather than some poor intern, right? This is what weak supervision allows us to do. So let's talk about weak supervision more formally and why it's becoming a hot trend in the industry right now. There's a paradigm shift happening in the AI industry these days, and that's the shift to data-centric AI. Weak supervision is one of the ways to actually implement a data-centric AI policy at your company. Andrew Ng, a very popular researcher in the AI field, defines data-centric AI as a discipline of systematically engineering the data used to build AI systems. What that means to us is this. Throughout the previous decade, the 2010s, there was a large focus on the AI ML model themselves. Our training data was collected once and kept fixed. Then we iterated with different models, different hyperparameters, etc., to get that incremental performance improvement. However, these days, with the advent of large scale models like BERT, GPT-3, etc., The models are pretty much becoming standardized and commoditized. Data quality has always played a part in ML model performance, but with the models becoming standardized, there are big gains to be had by engineering and iterating on the training data itself. In real world problems, changes to the training data can cause a change in accuracy of predictions by one order of magnitude more than any changes to the model parameters can ever give us. What that means is if you're changing the training data, if you get an accuracy change of plus or minus 10%, then changing the model parameters will only give you an accuracy change of plus or minus 1%. Hence, in the 2020s, this decade, we are going to see a lot more focus on data-centric AI approaches where we iterate on versions of the data to improve the performance of our predictions. As I mentioned, weak supervision is one of the ways to implement a data-centric AI philosophy. Snorkel AI, the Stanford research group that released the open source Snorkel library that we'll be talking about in the subsequent slides, they are currently a $1 billion company today. And I believe in the upcoming years, we'll see more and more investments in this area. So if I were to explain weak supervision in just one slide, it's this. Today's machine learning models ignores or has very less input from subject matter domain experts and places an unfairly large amount of importance to the knowledge of non-experts. But with weak supervision, we do not leave any knowledge out of the model. We can still use non-experts, but most importantly, we directly use the knowledge of subject matter experts to label and train our models. In essence, we use programmatic labeling sources to reduce the efforts of manual labeling while at the same time embed the knowledge of our domain subject matter experts into our ML models. From here on, the slides are going to get a little bit more technical as I'll be explaining how exactly we go about doing this, so please bear with me. This picture is a snapshot of the actual steps involved in weak supervision for your problems. In general, during the model training phase, there are 4 steps. We'll talk about each step in detail in subsequent slide, but at a high level, first we get our subject matter experts to describe their knowledge as rules that can be coded up using Python as labeling functions. Next, we combine the output of all the labeling functions using a label model. Third, we use the combined outputs of the label model as training data labels to fine-tune any downstream end model such as BERT or Robetta. And finally, we iterate the whole process. For inference, we only need the end model to make predictions. So in essence, it's no different from any other normal machine learning model that you would deploy for inference. So let's take a look at all these steps in detail now. The first step is the creation of labeling functions. This is the step that encodes the domain knowledge of our experts, of our subject matter experts, into Python labeling functions. So a labeling function is any Python function that takes one data point as input and returns either one label as output or abstains from labeling if it does not have enough information to output a label. For example, if we want to build a model that can detect spam YouTube comments, one labeling function could be as shown in the image here. If the phrase HTTP is present in the comment text, we call it spam. If not, we do not have enough information to make a conclusion, so we abstain. So basically, labeling functions can be anything. You can use keywords, heuristic rules, search queries, even the outputs of other models like zero shot or few shot models like GPT-3, BART, MNLI, etc. Also, you can use external databases. For example, for named entity recognition problems, you could use things like DBpedia. For named entity resolution, you could use Wikidata and so on. Constructing the labeling functions is super easy with Snorkel, as you can see in the code image below. You just need to add the decorator and any Python function will then become a labeling function. And one very important thing to take note is that the labeling functions are absolutely not expected to be perfect. It is, in fact, expected that the labeling functions will be noisy and far from accurate, but it's okay because the subsequent steps will handle that noise. Right, now that you have some labeling functions, you can start the second step, which is the label model. If we have n labeling functions, then each row of data will get a max of n labels, as seen in the picture of the table on the left-hand side. If we have 5 labeling functions, LF1 to LF5, then each row of data would get 5 labels. But to train our model, we only need one label for each row of data. The job of the label model then is to aggregate all the n labels into just one probabilistic label. As you might imagine, the easiest way to aggregate from n labels to one label is just to use a majority vote. But in the Snorkel paper, and the Snorkel library implements even better ways using some matrix mathematics. We'll talk about this when we get into Snorkel later. The cool thing to take note here is that coming up with the single label for each row does not require any ground truth data at all, and this was proved in multiple papers and in many real world experiments. But in practice, definitely a bit scary to not have any reference. So I always recommend collecting a small, maybe 100 rows of high quality hand labels, if nothing at all, but just to convince yourself and your boss and your stakeholders that you're doing the correct thing. This sample set is so small that you can get your domain experts to label for you. Just don't ask them to label 1,000 or they'll ghost you, right? Anyway, now that we have one label per row as output from the label model, this is basically our training data, and we can use this training data to fine tune a pre-trained N model. As shown here, the output of the label model is one weak label for each row generated by combining all the weak labeling functions. We need to use pre-trained models like BERT or RoBETA that have already been pre-trained on Wikipedia or all the text on the internet. Uh, yeah, basically the training data, we will use this weak label training data to fine tune a pre-trained N model. And transfer learning is super important to weak supervision because large pre-trained models that are trained on the entire corpus of the internet, like BERT, they already have a tremendous understanding of our language. We just need to fine tune the model with our weak training data, and the models will generalize even beyond the weak labels we provide to it. Since our labeling functions are programmatic, we can run them on the entire unlabeled corpus. So we can literally generate millions of rows of data and use that as a training data set. You can never get so many labels by hand labeling without spending a ton of money and time. Again, to reinforce what we've done so far is to encode the domain knowledge of our experts into Python functions and created a massive training dataset completely programmatically. With that, our model training is done and we can move to model inference. Model inference is rather straightforward. We only need the N model. We can treat it as any other BERT-based model. You pass it an input text data and you get predictions as output. But don't throw away all your labeling functions and label model work just yet. You can reuse them for model retraining at a regular cadence or model monitoring for performance degradation over time. We are in the realm of ML ops now, and weak supervision allows us to have a nice automated ML ops solution, as the labeling function creation work is a one-time effort versus hand labeling is something that is super difficult to automate. Right. With that in-depth understanding of the steps involved in weak supervision, let's spend some time to talk about a few very powerful frameworks you can use to implement weak supervision on your data. First is this paper published late last year called WRENCH, a comprehensive benchmark for weak supervision. The authors tested out many different kinds of label models and N models as shown in this picture. And they ran the test on many different standard benchmarking datasets as shown here, right? The red column is the baseline performance of a fully supervised model. This is the benchmark we want to compare our weak supervision approaches to. Top one is the best performing weak supervision approach on each dataset. Top two is the second best performing weak supervision approach on each dataset, and so on. Let's just focus on top one for now. The blue column is the performance of the fully weak supervision approach. And right off the bat, you can see that despite not using any label data to train, the weak supervision models, of course, with the appropriate labeling functions, because weak supervision is completely dependent on the labeling functions, the weak supervision models here can achieve performance that is quite close and sometimes even slightly better than the fully supervised models on many tasks. So just compare the values in the red to the values in the blue. So if we look at the end model, the column in green, then consistently we see that the RC and BC are showing up in top one. These are based on a paper called Cosine that we'll talk about shortly. RC stands for cosine Roberta and BC stands for cosine Bert. For the label model itself, the column in yellow, there's no clear convergence to one specific method and it can vary for each dataset. But the Snorkel implementation of label model, which is shown here as metal and DP, they appear many times, and so it's in general a good idea to start here. So yeah, one thing definitely to take note, very important thing to take note is despite not using any label data to train, the weak supervised models with appropriate labeling functions can achieve a performance that is close to the fully supervised models on many tasks. So this is the detail of how Snorkel works under the hood. To recollect, at the end of our labeling function stage, each row of data will have one label for each labeling function as shown here. So if you have 5 labeling functions, each row is going to have 5 labels at the end of the labeling function stage. Snorkel then uses this data to construct a correlation table where each column and each row is one labeling function, with the last column being the actual true label that we don't know but we want to obtain. So that is shown in the image below, the matrix image below. Lambda 1, lambda 2, lambda 3 are all labeling functions. So lambda 1 is labeling function 1, lambda 2 is labeling function 2. So you see here each column and each row is the labeling functions. So the whole matrix is basically calculating the correlation between each labeling function to every other labeling function. And the column in red, which is the correlation between all the labeling functions to the output y, is the metric that we want to estimate. So the values in the green box are basically the correlation coefficients of each labeling function to every other labeling function. This is easy to calculate from the table that we have above. Then the values in the red box, this is the ones that we want to estimate, and we can estimate them by treating this problem as a matrix completion problem. And this problem can be solved iteratively using stochastic gradient descent. So choose a random value for each box within the red column, then check how much is the loss, then change the values of each box in a direction that reduces the loss. So after doing this iteratively through stochastic gradient descent, eventually we will arrive at a value that can minimize the loss function. So in reality, all of this is done under the hood. So we don't really need to worry about it. We just call one line of code and Snorkel will provide such a summary table as shown in the Snorkel box here. This summary table measures the agreements and the conflicts between the various labeling functions. It's useful to see whether there are any bad labeling functions that we have to remove, right? So after this, we just call another line of code to run the stochastic gradient descent process and output the single label per row as shown in the green table on the right hand side. So at the end of this process, calling two lines of code, we have combined the 5 labels per row into just one label per row, which is exactly what our model expects for training. So at this step, we can pretty much use any downstream model like BERT and fine tune the model and use it. But yeah, one of the better ways based on the Wrench paper to train the end model is using the Cosine approach. Cosine is actually a very new paper, just published last year in ACL. It has a few steps in it. It's basically a method to train a downstream end model in such a way that it can reduce the noise coming from the weak labels. So let's go through these steps as intuitively as possible here. The first step is to use all the weak labels we get from our Snorkel label model to fine-tune a normal pre-trained BERT or Robetta model, right? This step is called the initialization step. So we just take the weak labels coming from Snorkel and directly fine-tune a BERT model. In the next step, we use this fine-tuned model to make predictions on the entire dataset. These predictions are then assigned a weight based on their prediction probability. So high probability is given a high weight and vice versa. Next, we take all the rows that have a weight higher than some fixed threshold. So basically those rows in which we have a very high prediction probability. So we take all those rows and uh, calculate a classification loss as well as calculate a contrastive loss. The idea here is that the texts that are similar in meaning should be closer together in vector space. So contrastive loss is a popular self-supervision learning technique that helps us to achieve this state. Finally, we add some regularization so that those rows with a wrong prediction but having a very high probability are penalized. So this is called penalizing for overconfidence. The row is actually predicted wrong, but it has a very high confidence that it is correct. So it's overconfident. We are penalizing all these overconfident samples by adding a regularizer. The final loss is the final loss of the model is the summation of these three losses as shown in the equation at the bottom of the page. And we continue training the BERT model with this compound loss. So once the model converges after several epochs of training, we can just take the pre-trained BERT model at the middle of this page for inference and we can ignore everything else around it. It's definitely a bit complex, but it works really well in practice to reduce the noise coming from our label model. Right. In real world testing, we notice that the performance of this kind of a weak supervision approach varies a lot depending on the quality of the labeling functions selected even before the Snorkel model. So in essence, the Snorkel math works with an assumption that each labeling function is truthfully tackling one aspect of the problem statement. But if there are some malicious labeling functions or labeling functions that are totally wrong, then they can poison the label model calculation and lead to poorer results. But the problem here is that we do not know beforehand which labeling functions are poisonous. So we implemented what we call a labeling function zoo and a heuristic labeling function subset selection. So what these concepts mean is the labeling function zoo is just a collection of several hundreds or even more labeling functions for each given problem that we're trying to solve. And similar to hyperparameter tuning, we then iterate over these labeling functions in the labeling function zoo. We iterate over them, selecting a subset of the labeling functions until we find a subset that gives us the best performance. So we don't use all the n functions present in the labeling function zoo. We only use a smaller subset of labeling functions that gives us the best performance of the n model. So we found this simple iterative approach works really well in practice to give us high quality models that can rival the performance of a fully supervised model. Right. So, yeah, these words are just describing what we mentioned. We just iteratively choose different subsets of from the labeling function zoo and run the process end to end and pick the subset that gives us the best model on the downstream end model. It gives us the best performance on the downstream end model. Finally, we have come to the end of this presentation. Let me take three more slides to wrap up. In conclusion, there is a paradigm shift towards data-centric AI on the horizon. Weak supervision is a great way to implement data-centric AI at your organization. There are four steps involved in building weak supervision. First, we need to encode domain knowledge of our experts into Python labeling functions. We can combine those labeling functions using the Snorkel label model. We then use the labels from the label model to train a downstream end model such as Roberta or BERT using the cosine approach. And finally, we iterate with different combinations of labeling functions till you get a good result. In terms of the frameworks, the best ones I've come across so far are Wrench for benchmarking, Snorkel for the label model, Cosine for the end model, and an in-house heuristic labeling function selection pipeline to select subsets of the labeling functions that give us the best results. As with anything in data science, these are only great starting points, but you'll definitely need to experiment on your data to choose the best ones. In terms of future directions, I'm currently seeing more research papers on a concept known as extreme weak supervision, which is basically trying to even automate the generation of labeling functions. So there was a paper even published by some researchers based out of Singapore called OptimSeed. We haven't experimented much with these approaches, but definitely something that's super interesting because right now the only manual part in the whole weak supervision approach is the creation of labeling functions. So if we are able to even automate that to a certain degree, then yeah, we can achieve even better levels of automation. Finally, there's a rise in UI-based tools for labeling function creation. Since the best people to create your labeling functions are the domain experts, they may not be coding experts. So these UI-based tools, such as the open source one from Rubrics or the commercial one from Snorkel Flow, these will come in really handy to get to get your domain experts on board to write labeling functions to train your weak supervision models. Last slide is links to more resources. If you are based out of Singapore and have a National Library account, you can borrow the Practical Weak Supervision book or ebook. It's not talking about state-of-the-art methods, but still a very good starting point for learning how to use weak supervision on both NLP and computer vision problems. With that, I reach the end of my presentation. Thank you very much, and I can take any questions now.